Welcome back. In this video, we'll get to know the current transformer model a bit further. In particular, we want to focus on the time-dependent sine curves. We know the meaning of the primary quantities already. We have also clarified what influence the magnetizing characteristic has and on what. Now let's look at the shape of the quantities inside the current transformer. Primary and secondary currents are displayed here. The primary currents are shown in yellow and the secondary currents in green. We can see flux linkage and the magnetizing current in this graph. The primary current has the same value as in normal operation or during a fault. That is, it's the current through the primary winding of the current transformer. The secondary current and the magnetizing current are multiplied by the transformation ratio Kr so that they can be compared with the primary current. We are going to use a dash sign for these quantities. The positive current reference system in the equivalent circuit diagram looks like this. IP and IS dash each to the right and IM dash down. Therefore, we can set up the following equation. IP equals to IM dash plus IS dash. The primary current of the current transformer is partly used for magnetization and partly transferred to the secondary winding. Now, with the primary current, everything is obvious. It is an exponential component described by the formula A times e to the minus t divided by Tp, and an alternating component with some other amplitude b multiplied by the sine omega t plus phi. This height is A according to the formula. The secondary current has a much more complicated shape, especially when the current transformer is saturated. Usually, in the shape of the secondary current, there are segments with the exact transformation and such segments in which the current transformer is saturated. Here, for example, it is clearly visible that this is a segment with the exact transformation when the current is transferred from the primary to the secondary side without losses. And here are segments in which saturation occurs. We can also see that the saturation happens almost in every period. As I've already mentioned, the shape of the secondary current depends heavily on the magnetizing curve. Let us recall how the simplest rectangular magnetizing curve looks like. There, the magnetizing branch is simply replaced by a switch. In this case, when this switch is closed, the secondary circuit becomes a short-circuited RL element. It means that the current that had flown in the secondary circuit before the switch was closed will decrease exponentially. Now we can look at a real oscillogram of a saturated current waveform recorded by a protection device. Here we can see also segments with exact transformation as well as segments where the current transformer is saturated. Followed again by a segment with exact transformation. We can see, however, that these segments with saturation do not resemble an exponent, since an exponent must decay but not cross the x-axis. Here though we can clearly see a crossing of the x-axis. Now how can this behavior be explained? This problem lies precisely in the rectangular magnetizing curve. That is, in the last type of the curve that we've explained in the previous video. This type of magnetizing curve cannot guarantee a transition through zero when the current transformer is saturated. Well, what must be done to correct this? We could apply the second type of magnetizing curve. We can try to actually simulate this behavior in the model. This type of characteristics allows us to take into account a residual inductance in saturation mode. This way we still allow the current transformer to transform the primary current into the secondary winding. Let's add a small time constant in the saturation mode. For instance, 0.1 milliseconds. We can see a small crossing of the x-axis here. If we add 0.5 milliseconds, we can observe that the secondary current now clearly crosses the x-axis, which is much more in line with the reality. The saturation time, shown in these plots, represents the moment of transition from one line to the other. That is the crossing of this knee point of the magnetizing curve. A crucial moment that I want to mention is the fact that the maximum initial value of the DC offset doesn't at the same time correspond to the shortest time to saturation Tz. Let us set the maximum DC offset in the model. Here we have the maximum projection onto the imaginary axis. From this graph, we can see that the DC offset is the highest, and the time to saturation is 10.8 milliseconds. Let's change the fault inception angle gamma now. You can see that the saturation time decreases, even though the DC offset is far from being the largest. Now the minimum saturation time is about 9.8 milliseconds. This behavior in the model corresponds to figure 12 of the technical report IEC TR 61869-100. This is a guidance for application of current transformer in power system protection. Let's open it. From this figure, we can see again that the currents in the first quarter period of the fault are higher for larger fault inception angles gamma than for smaller ones. Hence, the magnetic flux through the current transformer is also higher during this period, and the current transformer would saturate faster. I should also say a few words about the integral current values, which are represented in this plot by these slim lines. These are the amplitude values of the fundamental frequency, which were obtained applying a DFT filter over a full period window. For the model, we've chosen the amplitude values instead of RMS values, so that it becomes more apparent how the integral lines gradually approach the amplitude values of the sinusoids, and how saturation becomes less and less important for the measured signal. DFT means discrete Fourier transform, by the way. The window of the Fourier filter with the length corresponding to a full period at the frequency of 50 Hz signifies that in the event of a sudden current increase, the protection device will know a new reliable value of the current only after 20 milliseconds. Let us therefore briefly imagine that we have such a protection device that works according to this principle. Its current measuring time, the so-called pickup time, is 20 milliseconds. We now want to assess the behavior of the instantaneous overcurrent protection for the case in which the current transformer is saturated. As is well known, the overcurrent protection must have a high pickup reliability in order to make sure that the fault is cleared reliably. The pickup reliability is defined as the ratio between the minimum short circuit current and the pickup value setting of the overcurrent protection. We assume a factor of 2 for this ratio for our overcurrent protection, which is plausible in case of a primary protection. It means that the minimum short circuit current is twice as high as the threshold defined in the overcurrent protection. But our current transformer goes into saturation after 9.8 milliseconds, as can be seen in the model. This is 2 times faster than the pickup time. Let us assume that the project engineer calculates a saturation time of the current transformer for his project of 9.8 milliseconds. He then compares this time with the information given by the relay manufacturer and finds out that the pickup time given in the manual is 20 milliseconds, which does not seem suitable for his project at first glance. But let's take a look at what is actually happening here. As I mentioned a moment ago, the pickup reliability ratio is equal to 2, which means that the setting of the overcurrent protection is only half the amplitude of the short circuit current. I said amplitude because in this case it doesn't really matter. We can multiply the pickup RMS value by the square root of 2 and then continue working with amplitude values. So the pickup setting value looks something like this. You can see here that after about 8 milliseconds, the overcurrent protection already detects a value that is higher than the pickup value. It means that the protection device can already initiate a trip command to the breaker. And it is irrelevant that the overcurrent protection has not yet measured correctly, because its filter is only being filled with values. The protection already recognizes that the short circuit current is higher than the pickup value and is able to give the trip command. What does it matter then? That the current transformer is saturated after 9.8 milliseconds and the protection device measures correctly only after 20 milliseconds. In this case, one must rather pay attention at which point in time the value in the Fourier filter exceeds the pickup setting. In other words, making a decision about whether the protection device is working correctly or not without taking the pickup value into account wouldn't be a reasonable approach. The fact that the saturation time is less than the time until the short circuit current is measured correctly does not mean that the protection device will not trip. Therefore, each case must always be considered individually. After these 8 milliseconds, however, as we can see here, the value falls below the pickup value. Since we have an instantaneous overcurrent protection, this time difference here is sufficient to give the go-ahead to the breaker. Let's also add the remanence factor. For instance, 0.86. Now we change the fault inception angle to make sure that we have the shortest saturation time. We see here that the shortest saturation time is about 2.6 milliseconds. We can also make the observation that if remanence is taken into account, the shortest saturation time does not necessarily occur at the maximum DC offset, as can be seen on this slim gray line. Now, what happens here with the instantaneous overcurrent protection? If we had no saturation, we would reach the pickup threshold in about 5 milliseconds. But in fact, we have a crossing after about 20 milliseconds. This means that the overcurrent protection has been delayed by approximately 15 milliseconds. Well, for some projects, this would be an unacceptable delay. I myself am of the opinion that it would not matter in most applications. It is remarkable that in this example, the discrepancy between the saturation time of approximately 2.6 milliseconds and the pickup time of 20 milliseconds according to the manufacturer's manual, which so to speak indicates how well the protection device works, is so large that there is basically no connection between these two times. Now I have changed the fault inception angle in such a way that the value of the Fourier filter increases as slowly as possible. In this case, the pickup value is reached at about 70 milliseconds. This is already a considerable delay, although the saturation time here is 4 milliseconds, which is higher than the 2.6 milliseconds we had before. It means that for the evaluation of the instantaneous overcurrent protection, it is non-relevant whether the lowest saturation time was calculated or the maximum DC offset is present. The worst case for the instantaneous overcurrent protection is, as just shown, the minimum possible increase of the value in the Fourier filter. In this case, we get the greatest delay. The technical report IEC 61869-100 only limits itself to the specification of T-AL, the time until the accuracy limit on the basis of which the transient dimensioning factor KTD for the manufacturing of the current transformer is calculated. This time is essentially the same as the saturation time Tz, specified in our model. However, in order to be able to assess the actual behavior of the protection function, such as the instantaneous overcurrent protection in current transformer saturation mode, the entire course must be calculated, a feature that is offered by this model. As for the flux linkage plot, it's partly created for demonstration purposes and partly for those who want to delve a little deeper into the matter. The curve of the flux linkage has basically been calculated for aesthetic reasons. Here, the remanence before the fault occurrence is clearly visible. It's also easy to see how the flux hits the ceiling at this point, so to speak, because the magnetic core of the current transformer saturates and the flux can no longer rise. The same saturation behavior can also be set at the bottom of the plot. For the magnetizing current, in addition to the fundamental frequency, the second harmonic was also calculated, which is shown here with a dotted line. I'll explain what this was done for when we take a closer look at the differential protection. I think that I have sufficiently illuminated the topic of time-dependent waveforms. Feel free to comment below or ask questions, if there are any. It is best if you try the model yourself, in order to assess the real behavior of the protection. Thanks for tuning in. I'm looking forward to seeing you in the next video.